Hello, greeting, my friends. This is Dr. Mohamed Nezami coming to you from Jerash, Jordan. Welcome back. Okay, so we're going to continue on the design of optical front-end receiver. So let us share the slides and go from there. Okay, so last time, if you recall, the recording stopped, and so I had to split this into another session. But basically, this is the first part and the second part of this series. And last time we were talking about the the gain and level shifting, okay? And that's basically, we talked about how to take the optical sensor current, microamps, and convert it into voltage that is within the least significant bit to full scale capture range of the ADD, okay? And we did show that how the interface between the ADD and the transducer basically follows a linear function, which is AX plus B. Now, the slope, the direction of the slope, which is the sign of the gain, and the intercept, which is the DC offset in this case, varies. And last time, recall that we let's see, where did we go? Okay. Here it is. Last time we detailed these four topologies where the input of the optical sensor can be passed through so that we can present the signal correctly with the right polarity and the right range to the ADD. And we took this example here and we did looked at the simulations. And the second example that we looked at, one is here. And these are from application notes of ADDs, but we're using them in the scope of what I'm talking about, which is the interface between an optical sensor and an ADD. So here's an example. We have an ADD that has a range between zero point 0.5 volts to 2.5 volts, okay, and it's powered from 3 volts. The op amp in the middle, that we have a signal which is plus minus 0.25, no DC, just an AC signal that we need to amplify so that we can be within this range. So if that's the case, then 0.25, that's a half volt peak to peak. And we need to fit that so it comes in between this range. So usually the DC offset in here is presented so that when you don't have any signal in here, your sensor output is parked in the middle of the range for the ADD. So let's put this at 1.5 volt in here, okay? And then in that case, on top of the 1.5, we need to have this signal in here ranges from the minimum to the maximum, which is this range in here, which is 2 volts. So meaning we have 2 volts full scale to play with. So we're going to plus minus 1 volt in this case. So that's what we need to do here. So how do we scale or amplify the signal, the 0.245 volts peak, plus or minus to 1.5. And then we have a DC offset in here that we have to insert in the non-inverting port that has to be 1.5 volts. Let's solve. First of all, we start with this. We assume one of these resistors and we leave the other one so we can solve it. Okay. And like we looked at in this case in here, of course, if the signal is in the non-inverting port, we always have this gain in here, which is 1 plus the ratio of the two resistors on the inverting port. And then the one on the inverting port, of course, is just the ratio of these two resistors, okay? So let's do the same thing in here. So to get 0.25 to be 1 volt, okay, we need a gain of about 4. Okay, so 0.25 times 4, and that means the ratio of this resistor to this resistor has to be 4. And in this case, we chose 2K and 500 ohms, okay? Or the closest to it. So that gives us a gain on the non-inverting port of -4. But on the inverting port, the non-inverting port in here, the input in here, we have to fix this so that the DC offset is actually 1.5 volts. Well, the gain of the signal that comes in from the non-inverting port of the op amp is basically 1 plus the ratio of these two resistors. Okay, and the ratio of these two resistors, we did fix them to 4. So 4 plus 1, that's 5. 5 times some voltage has to be equal to 1.5, and that means it's 0.3 volts. So what we need to do, we would need to basically take this signal in here, do a voltage splitter in here that will produce 0.3 volts and feed it right in here. It's very important that this reference voltage in here is tied to this voltage, is tied to this voltage, so that if there is any temperature drift in the power supply or any variations, it all tracks so that it all adds up. And so what I did is I put this on the simulator, okay? And we were supposed to have 0.3 volts in here, and of course 2K and 499, and I put in 500 ohm as well in here because, as you know, always the impedance looking this way has to be balanced, although this has to be a little less because you have this in shunt with that. So when I ran this, and let's show you what happened, and that's why we need to make sure, always look at the op amp that we're utilizing and make sure this guy can go down to 0 volt and go up to 3 volts, as the circuit in here was suggesting, okay? So that we can go within this range in here. This range in here, of course, that's from the data sheet, okay? That we cannot do anything about this. If we need to vary this, then we have to vary that, okay? So here's the circuit, and if you run the DC calculations right now, just to see what, so the output is 1.5, so 0.3 times 5, that's 1.5, okay? And then the AC gain of this, let's see how much gain in here. We can check the AC response for that. And so we have this, and I did limit the frequency response with this cap, but if you go out here to the flat regions, 12 dB, which means it's 4. As you know, this is voltage gain. So it's a voltage gain, so this is power gain, I'm sorry. It's a square, so it's actually 4, meaning it's 8, really, power-wise. Okay, so this is working fine, but when we run this transients and we put in a 200 megahertz signal, the result is not really very interesting. This is the input, plus minus 300 millivolts, but we can see that lower rail clipped at 1 volt and the upper rail clipped at 2 volts, which really has to do with the op amp. So what I'm going to do first is increase this, so we do realize that the op amp really has a doesn't have a close to rail response. So if we run this again, okay, so again we can see that it did reach the maximum, which is 2.5 volts, and that is basically 2.5 volts because we do know that 1.5 plus 1 is 2.5. That's the maximum it can reach. Okay, but if you look at the negative, it still went to 1 volt. Okay, so which means really this one here, this signal here needs a more DC offset. So what I'm going to do is let's add make this 500 millivolt and rerun it. Okay. And we see that the signal right now is okay, okay? But what happens is the output in here, of course, if you look at the range, which is from this point to this point, it's 1.5 to 3.5 volts, okay? Which means we really did not achieve the this range in here, Okay, so but that's the reality. That's what you really what you would need. And of course, you can view this. Another way to view this is by let's go back to what it was in here, which is 300. Okay, and let's see what is really happening. Here is the you can go to the DC and get the transfer function. That will tell you more stuff. So we can see in here that when we reach about 100 millivolts, we're clipping at the this value. But and of course the DC offset is 1.5 in here. If this is 1.5 in the middle, you look how small this region compared to the other side, which is goes up to this much. You can see that it's not symmetrical. We need to move this point up here, okay, for this to be valid, okay? And that's why when you increase, for instance, when you increase this to 500 millivolts, now rerun this, okay? So now it's more linear because you can see that it really, the half volt is here, okay? And you can see that it has more range on this side to get to 1.5, okay? All right, so this is so really this what this tells you is that you really have to make sure that um, that you know the device. But one way to circumvent this, of course, is to utilize another op amp that can go real to real. Okay, so basically, as you can see, we see now that what we have to do, this interface business, is we always have to comply with this here, even though I did this empirically in here, but really there's more systematic way to do this from this function in here, because we know this function in here that if we know the slope of this, so we know the sine of this, and we know the DC level, so we can see which one of these do we need to solve, and then it's just two equations, two unknowns, because you got two outputs. We're giving the input range and the output range. So we do have two values on the input, two values on Vn, two values for Vout. So two equations, two unknowns, and you can get the M and B that determines the gain and the DC offset. And that's what we're going to do next. So basically, really realizing that these are the cases that you can be in, where you either need, in this case, where the sensor needs DC offset but doesn't need gain, or like in this case, where it doesn't need DC offset but it does need gain, or in this case or this case, which needs both the scaling, okay? And so really, one way to do this is we can generalize this with these amplifiers. So we can see that, for instance, we have one case where the DC offset and the slope or the gain is positive, and that's this circuit in here. That's where we have the input and the reference is both on the non-inverting port. And the output in this case, of course, is really we have it's a non-inverting op amp, so it's always going to be 1 plus the ratio of these resistors as your gain for both this one and this one. The only difference is that, of course, the DC level in here, this reference in here, is split between these two resistors at this point. So to solve this equation for this case, V out is equal to Vn multiplied by, first of all, is the gain that comes in from these two resistors in here, which is Rf plus Rg over Rg, which is the same as 1 plus Rg over Rf, okay? Plus, this voltage in here gets split at this node in here. So we have a voltage divider between R1 and R2. So this is the AC gain. Now the DC gain, which is this gain in here, the gain for this one in here, is basically the same thing. We do have this in here, which is basically this ratio in here, which is 1 plus that. And then we have a voltage divider that divides this DC between these two resistors right at this point, okay? So we have this equation, And usually what we have is we have 2 points, okay, and two inputs, two VINs and two Vouts. And that's two equations, two unknowns. And we assume R1, we assume RG or RF, whichever one, and then we can solve the other two resistors. The other case, of course, is when you have a negative DC offset. And that's basically all you need to do is just put the reference on the non-inverting port, because I'm sorry, on the inverting port. And your input would be on the non-inverting. So in this case, this one here is MVN. Okay, this is VN with a gain coming from these two topology in here, minus the DC offset that comes in here. And that's basically solved by this equation here. So we've got VN, and then what we have to do is we have to RF um, over the combination of this here, which is this resistor plus the prior combination of these two. Okay, so that here over this one, and what if you look at this, that's really nothing but 1 plus the ratio between RF and the overall combination of these impedance looking into this port in here, which is RG plus the prior combination of R1 and R2. Now, as far as the reference voltage, oh, I'm sorry, that's this one here we're talking about. This is negative. The input is the same way, except it's positive. Okay, and we can do the same thing to the other two, one where it's negative gain, but the positive reference. So the reference is on the positive port, and then this one on the negative one. Okay, and this one is much simpler because VN goes in here. So this is just an inverting op amp, which is just this ratio, this resistor over this resistor plus. Now this voltage gets divided between these two resistors. So the first thing is we have to multiply it by this, okay, to get the actual voltage in this point here. And that point here is actually gained by 1 plus the ratio of these two resistors, and that's right here. Okay, moving on, one where this might be, okay, this is the last one, which is both are negative. Okay, in that case, then we put them both on the inverting port. Okay, and in that case, it's just the ratio of this resistor to that resistor, okay, on both sides, and of course, negative. And I did plot all of these to show you the difference in shape, okay? And so how do we decide on this? This is basically from really your sensor, the natural behavior of your sensor gives us that. Okay, so let's take an example, okay? So basically, here's an example. I'm giving a circuit where I need to interface a sensor that has a voltage level from 10 millivolts to 1 volt. And then I want the output 1 to 4.5 volts, which is typically from ADCs that are powered from 5 volts. Okay. And so what we need, we start out at 1 volt so that we are up in the clean region, way above the least significant bit, so that we can give room to the negative rail to have more headroom. Okay, so the first thing we need to do is we need to solve V out as a function of these two resistors and these two resistors. So we do that. Once we do that, we equate that to a linear equation that is using these 4 points in here. Okay, so the output in here will be MVN plus B. Okay, and VN in here, which is this one here. Of course, the gain of the non-inverting non-inverting op amp is really nothing but this one here, which is 1 plus RF over RG plus 1. Okay, RF plus RG, the ratio of this one to this one plus 1, that's a gain for both of these signals in here. Okay, so we see that, except in the VN in here really has a voltage divider because it's divided between these two. So that's what we would do here. Okay, so we have it gets divided in here, And the same thing, this one gets divided as well. So we have, except in this case, they're different. They're coming from different direction. The voltage divider that has to do with VREF, we multiply by R1 over R1 plus R2, this one here. But when we go to VN, we multiply R2 divided by R1 plus R2, which is this one here, okay? And of course, we have the gain due to these two resistors. But that here, let's keep this in mind. But what we do, we have the ADD input or the output in here is MVN plus V. We have 2 points. We have 1 and 4.5, right? These V outs, two values for VADC, these, which has to do, we equate that to M times this input in here plus B, and M times this input in here plus B. So we have two equations and two unknowns, M and B. Well, first of all, let's cancel one of the unknowns, and we can do that by subtracting these two equations from each other so that we cancel out the B. If we do that, we automatically get M is 3.535, and then take this value and substitute in either this equation or this equation, you get a value for B, and in this case, it's almost 0.96, okay? So the final signal that has to equal to this here is equal to 3.5 volt VN plus 1, okay? And it's positive. Now you take this here, this 3.5 has to equal this portion in here, and the one has to equal this portion in here. All of this, including VREF. Okay, so we assume R1 and we assume RG, and then it's just a matter of solving R2 and RF, and that's what you need to do. So basically, you take this equation, you equate it to this, you substitute R1 is, let's say, 1K, and RG is 1K in this one. So you're left with just two unknowns, okay? And then, of course, you can solve for them, okay? So you assume one of the ways to do, the first one where you drop off is you let Vn equal 0, that removes this one completely and gives you this. So we know that B has to equal that, and you can solve for one of those values, okay? All right, so let's go and put this on the simulator, and that's what I did in here. Okay, so here's the circuit. Here's the circuit. Okay, so basically we got Vn in here, okay, with these two resistors, and we've got the reference in here as well. Okay, and then this is the feedback. Okay, and I did solve this myself, and this is what we get. So we have from 0 to 1 volt, we're going from 1 to around 4.2. Okay, or close to this. Okay. And you can see that with an AC signal as well, and the gain as well. You can see it in here. So let's run this. Okay, so let's do this. So we have this one here. So the first thing is need to do is just calculate the DC point. So 2.5 volts. That's the DC offset right now. Oh no, sorry. Oh, this is the other circuit. Let's see. Where is this? Okay, so the file is 20. So let's load up that circuit. Okay, so here's the circuit, and zoom in so we can. Okay, so we got this is VN in here and the reference in here. Okay, and so let's do first of all, let's do this one here. We can see that 2.73. All right, so let's do. Let's get the AC response first, or the DC. Let's see the DC characteristics. Okay, so this is the DC characteristics. You can see that it's linear between, that's 1 volt, 23 mils, to 4 volts, okay? And so it's not reaching out to 4.5 volts quite, and that has to do with the op-amp really. If you really need to solve this, you need to add a little bit more DC on the signal. Now, the value of B, of course, you can see it very simply by going to the zero value in here, which is this one in here. And that's basically 1, okay? In our case, it was 0.96, which is close. I mean, you can go down here lower to see it. Okay. All right. So let's look at the AC response of this transients. And I have a 200 megahertz signal in there. Separate. Okay, so you can see that this is the output. This is the maximum, 3.7 right now, to this one, which is 1.5. All right. So we can see what it's going between the ranges, and that's correct. So anyway, so let's go further. Okay, so now let's get back to the block diagram in here. Where is the block diagram? Okay, let me see. Okay, this one in here. So we know that we what we did is we saw how you would have to TIA we produced last time in the last lecture. So that one you can't have anything to do with that. You don't want to mess with trying to fix the offset and the gain all in here. So that one really is more tight with the optical sensor. But we have seen how you manipulate the DC offset and the gain and the slope or the polarity of this stage in here. Now, this could be, of course, single-ended or differential. Okay. And so in a lot of cases, we're dealing nowadays with differential amplifiers driving ADs. And if that's the case, nothing changes. Everything I talked about for single-ended still applies, but you have to do it with the fact that you have a differential amplifier. And differential amplifier is nothing but really a 0 and 180-degree signals at the input and at the output. And of course, the beauty of that is that any interference comes in common to any of these components, whether it's leakage from the power supply or it's radiated. It gets canceled once it goes into the A to D because one of the branches is this lower one is always 180 degrees out of the other one. And of course, we're driving them out of phase on the input. So when we go to the output, the desired signal doubles while the undesired signals cancels. If assuming that we do have a common a reasonable common mode rejection ratio. And of course, the top half is exactly the same as the lower half. And of course, talking about gigasamples per seconds devices, nowadays you really have to do, there's a lot of effort on the layout to try to balance these things, okay? So basically, differential for simply, if you have an input here, you split it to two parts equally, but out of phase. And then what happens on the output? You get exactly the same two signals, except they are gained and DC offsetted. Okay. Like in this case, this is a common voltage, 2.5 volts. Okay. You see the same signal, but it has the gain, which is the ratio of this resistor to this resistor on both ends. And this resistor had to be like 0.1% tolerance so that you try to preserve the common mode rejection ratio because you really need symmetrical components, frequency response and values. So just to remind you of the benefits of differential ADC drivers. Basically, they improve signal integrity by enhancing noise immunity. Because of the rejection of common mode noises on both interferences and noises gets canceled, and then it provides a wide dynamic range, okay, swing because it basically you're dividing the input voltage to two parts, two separate amplifiers, and then of course reduces the harmonic distortion. This one you can check your out of box how it does that because when you have a balanced amplifier basically the odd and even, because when you square something, if it has a sign, the sign gets removed. And we subtracted differences, differential. These things that have even powers, they cancel out, which means second harmonic, fourth harmonic, and so forth. And then provides functions such as like what I have been doing, which is to control the slope and to control the DC offset so that you can drive your outputs to whatever makes this thing happy in here. Like for instance, in this case, the ADD is driven by 5 volts, so the middle is 2.5, and so that's why this one is 2.5 in the middle. Okay. And then of course, you control the gain so that you actually within the dynamic range of this ADD. All right, this one I didn't correct it, but let's go with it. This circuit in here doesn't correspond to these, but let's just show and imagine if these resistors were these resistors in here. I didn't get a chance to correct this one. First of all, the simplest way to do a differential amplifier is to take a signal and then buffer it, okay? And take the output right here. So that's your output, one of the outputs, the positive output. And then you can take the same signal into an inverting amplifier, okay, and then go out. And that's basically your negative, okay? So either way, really regardless, these are just names, okay? Um, so what you would need to do in this case is you have to have very tight tolerances on these. And also you have to make sure that, for instance, when you're doing this way, this has a gain of 2 in here, of course. So this is twice the input. And then I have a little DC offset in this case, 625 millivolts. That here gets gained by that's twice, doubles, okay? Oh, I'm sorry, the gain in here, yeah, it's 2, okay? So this one in here doubles, and that's 1.5 volts in here, and 1.25 in here. And that's why we're using 1.25 as well in here, okay? So, and this one, same thing in here, so this ends up 2.5 volts. Now, the V out in this case, okay, in here is equal to the following. First of all, you got these two resistors, the ratio of those two resistors, okay? This is an inverting amplifier, so that's these guys in here. That's this term. And this one is negative, of course. Now, as far as the reference voltage, which is in here, okay? So we have two things. This input, once it goes in here, it has a gain of the ratio of these two resistors. Okay, that's this way here. That's this guy here. Okay, so I think these are reversed. Okay, so this one, the plus one, is really this ratio of these two resistors plus one. No, that's this case in here. I'm sorry. So this is correct. Okay, the reference voltage, which is here, we have 1 plus this ratio. This gets to here, and that's the DC. Okay. All right, let me just correct that. Okay. Okay, there was a little confusion here. There's some errors in this equation. That's why I put this line. I try to put a text to this, but let's just take the concept as we look at this. So what we're trying to do, we're trying to create a full differential amplifier drive in ADD using discrete components. So first of all, we take the input, we go in here with a certain DC, and we establish a signal level. And then that signal level, that very same thing, what we do is we take that and create 180 degrees out of phase with that. And those should be, two here should be equal, and therefore an out of phase. And that's basically your differential amplifier. Now, the V out in here is presumably Vn, although in the way this diagram is, it's really twice Vn, okay, because you got a gain of 2 coming from here. And then, of course, the DC offset that comes out of here, you got, in this case that I have here, when I drew this, this was 0.62 volts in here, and that also has a gain of basically 2, so that's 1.5, and that's why I have 1.25 in here, and this is 1.25. Of course, this one in here also has a gain of 2. So this will be here is 2.5. But of course, you subtract from it the one that comes in here, which is 1.25, and you end up with only 1.25 at the output in here. And the same thing in here. So it balances out, okay? And that's what you need to do. So you need to discrete components. And of course, this is one way to do this, is if you're trying to do it discretely with 2 separate op amps. But really, nowadays, there are some fully differential amplifiers that are available, and I'll show you in a minute an example of this. So the output of this basically is really the whatever the signal in here, it's amplified by this resistor over this resistor, because this is non-inverting. This is an inverting amplifier. And in this case, this has a gain of 1 here. Okay, it has to have a gain of 1 because this is where this signal in here, we're trying to make sure it's equal to that signal. Okay, but of course it's inverted 180 degrees apart from this. And the DC level is, it works out that this DC offset in here is equal to this DC offset in here. So to try to prove this, if the designators were correct in this, because from this equation I could see that these resistors were swapped. What we need to do, we have V out equal V in, and then V out positive, okay, and then V out negative, we solve for it and subtract them from each other. That gives you the differential output, okay, which should end up being correctly. And then the common mode, of course, you sum them and you divide by 2, which is the average. Okay, so let's put the circuit on the simulator and let's play around with this. So, and that's what I have here. So first thing is, you can see this is 0.625 volts in here, and this is an AC signal that goes in here. There's a gain of 2 should be here from this circuit, okay? So the overall gain of this circuit is really 2, voltage-wise, okay? And of course, let's see, the DC gain, the DC also should be 1.25 in here or so. So let's solve the DC levels first. Okay, so there we go. We got 1.25 volts in here, 1.25 volts in here. The minimum is very tiny, it's microvolts. So you can see that it's got 60 dBs of common mode rejection between them. Okay, now let's see the, okay, so let's see the AC response of this circuit, of course, as you can see here. So we've got, if you read this one in here, it's 4 dB, and that's really the gain of this network. Okay, so let's do the AC response, and let's see what happens in here. So this shows it better. So we have an input, which is this. It's plus minus half volt. Okay, that's basically what this is. And that's what I have in here. So it's 100 megahertz with a half volt in, okay? And then what happened, of course, we've got, I have a label, which is, let's see, V out, V negative. So we've got V in and this, and V out, you can see that it's here. So here's one, and here's one, the negative and the positive. And you can see they're out of phase, and there's a little delay in them, between them. So we have to work on that. So if you look at the maximum in here, 1.25, and this one, okay. And so the difference, of course, is this here, which is really nice. So the output between them is the output swings about 0.8 to minus 0.8. So which is really good. Okay. All right. So this is what we have. So let's continue. All right. So next thing is I have another example. Let's look at this example. Now, again, this is from ADD handbook for ADI, and this is a, a real circuit type. So we've got an ADD in here that we have. It's AD92 something. The part. This is an older part, but it's just we're illustrating the example in here, the concept. It's powered from 5 volts, and it's got it provides a reference voltage 2 volts. And we're taking that 2 volts in here, and we're going to implement something like this, okay, using two op amps. Using in this particular case, they're using this in here. I've got plus minus zero point 0.5 volts in here. The thing we need to do is that this is 5, so preferably if we can get this point here and this point to be at 2.5 volts, but in this case they chose 2 volts, okay? So what we need to do first is we need to take the 2 volts, we split it first into 1 volt with these two equal resistors, okay? That 1 volt, we feed it in here, and whatever the output comes in here, okay, these are two RC filters. There's low pass filters. Just ignore these for right now. It has nothing to do with what we are talking about. So we have the signal in here, it comes in, and we go into a non-inverting amplifier, and we have with a gain of 1. So that created at this point here, that created a 180 phase shift with the input. Okay, and then the same thing in here, except since in the non-inverting, and we have two equal resistors. So in here, so that's basically the gain of zero point 0.5 volts. That's a gain of 2 in here, and that gives you 2 volts. Okay, in this case in here, so we've got the signal in here, and we have a gain of 1 in here. All right, so we got, oh, okay, no, we split, this is, oh, I'm sorry again. Oh, okay, hold on. The DC offset from these 2 points has to be 2 volts. So we're taking 1 volt, okay, with two equal resistors. That gives a gain of 2 for the non-inverting port, which means it's 2 volts, okay? And the same thing we do in here. We bring in the 2 volts in here, directly in here on the non-inverting one, okay? And that basically comes out here. So now we need a gain of 1 in here, and we need a gain of 1 in here, okay? So that the signal is basically, no, the gain of 2, sorry. This is a gain of 2 in here and a gain of 2 in here, okay? And that should work. So let's put this on the simulator, this very same circuit. And that's what we get in here. So let's go to the simulator, we can see it better. So we have a circuit in here, and then we have the input-output relationship DC-wise, because this is DC coupled. Now, one of them would be positive slope and one would be negative slope, so these are differential. When we subtract them, or we end up with this here, which gives me, so from minus 0.5 volts to plus 0.5 volts, it gives you from minus 1 to 1, which is what we need. Okay, so let's see. This one, of course, 11. So okay, so we got the circuit in here. All right, so we've got this in here. First thing is, let's see how balanced this is DC wise. Okay, so we have 2 volts in here, 2 volts in here, which is good. Okay, so meaning it's balanced. So, and then the other thing we need to do is, let's see, AC wise, let's see how much gain. Of course, this really has has a gain of 2, right? So we should get, Uh, okay. All right. So if we go to the flat region, it does have a little peaking, but we can ignore that for right now. And it has 6 dB, okay, which is the power gain when you double the voltage. Okay, so that's correct. All right. So now let's look at the transients. All right. So it looks nice. So basically, before I separate the curves, you can see that this must be the differential signal because it's in out of phase and in phase. And the large one is basically the difference between them because we subtract this from negative negative that, which means you end up doubling. Okay, so the difference is this. And if we look at this, it should be from +1 to -1. Okay, there we go. And of course, the Vn is plus minus one half volt. Okay, and you can check the DC offset on the input on the both of them, which is 2 volts. So we did match uh, that circuit in here, which is basically creating a fully differential amplifier from a discrete op amps. So again, whatever the input that comes in here, that gets twice in here. So which plus minus 0.5. Um, okay. All right. Okay. All right. All right. Okay. All right. So like I said, I mentioned this before. There are some available devices that you can purchase which are balanced internally. So all you need to do to hook them to the ADD is basically bring the device and just put um, your resistors outside and provide a common mode voltage. It does provide you with, like in this case, this device in here, LMH 5401-SP. So you can see this device in here has some internal resistors. Okay, so all you need to do is just add those resistors on the outside and then basically end up with a fully differential amplifier. Okay. And I believe I did, okay, so here it is. I took this from, there is some reference design files for this on TI site. And so I brought this in and you can see that in here. So that's circuit 12. Let's see, close this. All right, so we got this here. Okay, so all you need to do is we got the feedback in here, the positive feedback and the negative feedback, and you stick that, it's the RF basically, that's a feedback resistor. And this one is an outside resistor, but there's internally another resistor in here. So basically when you have to take that into account when you take the ratio of these two. Okay? And I'm providing 2.5 volts in this case in here as a reference. Okay, so this is modeling the differential um, load of the ADD. Okay, so let's see DC wise what do we get on this guy here. You can see it's balanced fully. So okay, so and then AC wise, we can look at the transfer function. Okay, so you can see this is a real nice device. Goes all the way to past a gigahertz. Okay, so you look at the flat region. This is about a gain of 10 right now, dB. All right, 12 dB. Okay. All right, so let's look at the AC response, and we can see that right here. So you can see that here's the input, plus minus 2500. Is it 2500 millivolts? Yeah, 250 millivolts. Okay. And of course, the output, you can see these are this is the output. This is a differential. Okay. So we're going between this value and this value, which is a swing between plus and minus one. And of course, the V F1 and F2, that's basically the measurement. I'm measuring these points in here. Okay, so you can see them. There are face, really nice match. You can see that there is definitely a benefit to utilizing these devices. The only fear all the times is that they could go obsolete once in a while if they are complicated like this. Where the other circuit discrete components, you can use very popular old devices that has been in there for a while. All right, so this is another one, another example that I took from TI site. You can cascade these and get much higher gain, and that's 13. So let's see, open 13. All right, so we've got this here. Uh, that's this device basically. Again, it's fully, we go from single-ended to double-ended, okay, out of here. And then we amplify double-ended and go into the ADD, which is modeled by these two resistors in here, okay? So if we, let's see, if we go AC transfer function, all right, wow, we get a very wide band response. And this is the gain from each stage. Okay, so here's one, and then here's the second one. Okay, so um, all right, okay, all right. So that's this here, which is nice. Okay, let me go back and look at the AC response. This. All right, so you can see here that look at the now how nice differentially this is symmetrical, and the output is of course is doubling. Okay, so you can see that it's this is the input, and this is the I didn't draw the differential output, but you can see this. All right, so okay, let's see what else. Okay. All right, so we go to the next topic, last topic. Okay, before we introduce the last thing, this is showing you a block diagram of a typical front end for high frequency sensors. This could be very much be the signal from an antenna that has been amplified through a low noise amplifier through some preselectors and fed directly into this because these ADDs are gigasamples per seconds. But this shows you how these amplifiers, this differential amplification is done for a sensor signal in here. And even this one here uses a programmable DC offset because really you can steer this, you can optimize, keep track of the signal so that you always try to center it into the ADD and capture range. Okay, so this shows you a typical ASIC front end, either from TI or ADD analog devices. And so you can design these based on the Nyquist zone to whatever you want. And this shows in here these devices, LMH and LMH 6000, 5000. These are devices from TI. Okay. And so to do this, this is fully differential, and you're going to start now at this point departing from treating this as an analog circuit and going to really become an RF engineer, and that where you have to design it. And these are some examples of these, how they're designed basically. I start seeing inductors, of course, because these frequencies that you're driving the ADD, you're going to have to resort to either passive LC filters or ceramics or microstrip filters. Okay, so it's pretty simple. You come in single-ended. Use a balun to create your input to the differential amplifier, and then you equally on both sides of the rails you can drive your ADD. Of course, your ADD has a common voltage that you have to provide. In this case, you have to provide it as a common voltage source to the amplifier itself because this is DC coupled. But if you're AC coupled, you don't need to do that because your signal can swing anywhere it wants to. So now all you need to do is just recreate insert the DC offset right at this point here. Okay, different values. You can find from TI bulletin boards and discussion boards, you can find a lot of these examples in here. And I did capture these from TI sites. All right, so let's get back to my initial design, which was TIA, this device with a voltage amplifier in here. And let's try to, basically, this is what I had before, and it worked fine. The signal was, this is how it swung, a little bit less than plus minus 1 volt. Okay. And so the input was from 300 microamp to plus 300 microamp, and the output was basically close to one plus minus 1 volt. And I'm going to take this and add to it a differential amplifier, basically, because I need to drive an ADD differentially. So what I'm going to do, I'm going to take this signal and create a stage use to go from single-ended to differential, and that's what I did in here, and you can see that it did work fine. So let's go to that and see, and you have it rolls a little bit before a gigahertz. Okay, so let's go take a look at that. That's let's see. I wonder if I put the DC voltage. Oh, that's 3 freeze, I think. Oh, yeah. Okay, so this is basically this is what I did. So I have my ADD input is assumed to be like this here without any parasitic capacitances. And I took this device and interfaced it to my other amplifier. So my TIA that was designed in the part one of this series. So first of all, I want to see my DC points. So I've got 2.4 volts in here, 2.4 nice millivolts in here. Okay. And of course, this is negated from this because this is an inverting device. So let's look first. Let's see. Let's look at the AC response of this. Okay, so basically here's where I am. It does starts to roll off at around 200, 300, 400 megahertz onto a gigahertz. Okay, that one at a gigahertz has about a gain of 71 dB. Okay, so and then of course we need to look at the response. So let me put let's look at the DC characteristic equation. Okay, so basically you have oh, it doesn't mean anything because I'm really AC coupled in this case, so that doesn't mean anything. Okay, so let's look at the transients. All right, so this is nicely how it is. So you can see here that this is the differential ported signal in here. This must be V F3 and F4, and the tiny one is the input, and then of course the other one is the. So let's see this here. So let's start with this. So I've got a an optical sensor in here that has a plus minus 200 microamps input, and then basically my output, which is at this case here, this voltmeter, AC voltmeter is this here. And if you measure that, that is the swing on that is basically, okay, so plus minus 1.3 volts. So that's very good. It's a swing of 2.5 um, volts. And the AC signal, the DC is very tiny. Okay, the VF1, VF2, that's the differential signal. And let's see, VF3 and VF4. This is the VF3 and VF4, which is the output in this. So if we measure one of them, this one here is going between, okay, 2 to 3 volts. Okay, so the DC on that one, on the VF4, that's this guy here. So that's about 2.5 volts. Okay, and the same thing on the other one as well. So if you, let's measure the other one. Yeah, it's 2.5 volts. Okay. All right. So this is nice. This is ready. So this task is achieved. Now you can make this into bandpass if you want. Just add a little LC suction in here, and that's what I did in here. So you end up with something like this. And let's go get that and look at it before we close the session. Okay, so basically I added this LC section in here that does the shapes the frequency response so that it's more like a bandpass filter to the A to D. All right, so here we go. Okay, it's hard to see it once it's okay. All right, so it rolls off between the lower cutoff is like in the kilohertz, hundreds of kilohertz, all the way to uh, okay, that much in there. Okay, so uh, this really closes this session. So basically, in this part, what we did cover is we covered the this portion in here. Okay, I hope this gives you a clear picture of what is really involved. But so far, really, the interesting thing is that this is really fully analog, even though it's in the gigasamples per seconds. But really, eventually, you still need to treat this as an RF board and layout and design as well. In fact, these devices most of them, they give you the S parameter file. So you can actually, because you still need to match this device to a filter in here. And same thing in here. So this is does. Okay, so next, what we're going to talk next is the last session is the noise aspects of this. What happened to the noise? Is this diagram in here? That's really what we need to analyze. How do we keep track of the signal to noise ratio throughout all of these? Now, you could see that I gave you the methods of trying to pull the signal power level from microamps all the way to volts, few volts, to drive into the A to D. But what happened to the noise? Did we preserve the signal to noise ratio? Now, you cannot get free noiseless amplification. That's definitely is always the case. So how do we go into that next? Is that I'm gonna try to model this so we can look at the noise. And right when you start looking at the noise now, we're gonna get into the aspect of noise density for these devices. So we do have the noise density for all these devices, okay? And the ADD, we have to start look at its noise density as well. And the trick is we have to make sure that the noise in the background in here, thermal noise, is has minimum amplification until we get to the ADD, and then it doesn't do us any good to have that noise background below what the ADD can see, because we really don't need that. We need to get it up so that because we're losing gain, or using too much gain in this case, we need to bring the noise level up so that it's right at the at a certain margin above the internal noise density noise of the ADD, and that noise, of course, in our case, is really the quantization noise of the ADD, because it cannot see beyond a certain plus minus half least significant bit. And that least significant bit is a function is a function of the resolution of the ADD, how many bits. Okay, and so we're going to start looking at that and look at the noise contributors to the signal in the DSP domain, and that is really comes in from the reference voltage. This guy in here puts noise into here. This guy puts noise, this guy puts noise, and there's thermal noise from the outside. So we've got thermal noise from the outside. We've got the noise that is the KTB noise of the system that comes from the outside. And then we have the noise that is internally generated within these active devices in here. And then we have the spectral noise density of the ADD. Okay, so take all of these and combine them with the square root of the mean squared for all of them, because as you know, these are non-coherent noise sources, so the power adds up in means, not in coherently. Okay, so that's basically what we're going to talk about. So until next time, ladies and gentlemen, this is Dr. Mohamed Nezami. I wish you a great um, day, and hopefully that last session will be more enjoyable to you. And if you have any comments, let me know so I can bring up other topics that you may be interested in. So again, thank you very much and have a great day.